Everything in the universe undergoes a process of formation, development, decline, and eventual end. From tiny human beings, planets, stars, galaxies, or even larger nebulae, none escape this cycle. So, have you ever wondered, will the universe itself, the container of all things, ever reach its conclusion and return to the moment before the Big Bang? This is a truly profound question, currently beyond the limited understanding of humanity. Hey guys, tonight we are going on the ultimate field trip, a journey not just through space, but through all of time, from the very beginning of everything to its eventual, quiet end. We're strapping into our mental time machine and diving into the incredible, impossible story of the universe itself. Imagine standing right at the edge of existence, gazing into the void before the Big Bang. It's not dark, because there are no photons yet. It's not silent, because there is no medium for sound. There is simply nothing that we could recognize. Yet somehow, all the potential for trillions of galaxies is compressed into a space smaller than the period at the end of this sentence. You probably wouldn't survive this era. The conditions are a little rough, unless you're a neutron or maybe a free-floating electron having a bad day. But don't worry, we have a cosmic force field that lets us observe without being incinerated or compressed out of existence. Now, picture that unimaginably dense point, what physicists call a singularity. It holds all the energy that will ever exist, all the matter that will ever form, all the space-time that will ever stretch. It's the ultimate cosmic starting line. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And if you're joining this cosmic cruise, why not drop a comment with your location and local time? It's fun to see how far and wide this story travels. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's drift into tonight's story together. The clock is 0. Then, in an instant, less than a nanosecond, a moment of unbelievable, explosive expansion occurs. This isn't an explosion in space, it is the explosion of space itself. This is the Big Bang. You aren't seeing fire, you're seeing space-time stretch faster than the speed of light. A process called cosmic inflation. Historians still debate whether inflation was driven by a scalar field or a vacuum energy shift. But for you, it's a moment of sheer, mind-bending speed. The universe grows from subatomic size to the size of a grapefruit almost instantaneously. Try to imagine scaling up your living room to the size of a galaxy in the time it takes you to blink. That's the kind of cosmic growth spurt we're talking about. As this rapid expansion happens, the universe cools slightly but remains incredibly hot, a dense, fiery plasma that is still far, far hotter than the core of our current Sunday. This is the first second of the universe, and it's a blur of activity. All four fundamental forces that govern everything we know, gravity, electromagnetism, and the strong and weak nuclear forces were unified, acting as one single superforce. Think of them as a team of superheroes stuck together in a tiny phone booth. But as the universe expands and cools, gravity peels off first, gaining its own identity. About 10:43 seconds into the journey. It's the first rule in the cosmic playbook. Gravity is the boss. You are floating inside a primordial soup of pure energy. No atoms exist yet, not even the nuclei of atoms. We're talking about the most basic building blocks, quarks and leptons, zapping around in what's known as the quark-gluon plasma. It's so hot and dense that light can't travel more than a tiny, infinitesimal distance without bumping into a particle. It's like being inside a fog so thick it's actually opaque. This super hot, turbulent period, which lasts for the first few minutes, is where the stage is set for everything to follow. A curious detail about this era is the slight, almost imperceptible imbalance between matter and antimatter for every billion particles of antimatter. there was 1,000,000,001 particles of matter. That tiny surplus, the one extra particle of matter, is what survives to make up you, me, the Earth, the stars, and everything we observe. Thank goodness for that tiny bit of overachievement. Otherwise, we'd have a beautiful, silent universe of pure energy, and no one to watch it. You are still swimming in that super hot, turbulent cosmic soup, though the temperature has now dropped enough for the next phase to unfold. We are roughly 1 second to 3 minutes into the universe's life, and it's a phase of rapid change, where the laws of physics you learned in school start to make sense. Remember that initial chaos? Well, now things are starting to settle down, but only in a very high energy, relativistic kind of way. First, the weak nuclear force and the electromagnetic force finally break their bond, leaving us with the 4 distinct forces we know today. Think of the universe as a complicated machine that's finally getting all its gears in place. At this point, the temperature is still ridiculously high, about 10 Kelvin hot enough to fry a diamond. If diamonds could even exist. Yet, spoiler, they can't. You're surrounded by a dense, swirling cloud of quarks that are now starting to feel a powerful attraction. The strong nuclear force. This is the moment of nucleosynthesis. All those free-floating quarks finally get their act together, combining into particles called hadrons. The important ones here are protons and neutrons. Protons are stable, but free neutrons have a notoriously short lifespan, about 15 minutes before they decay. Because the universe is still so incredibly hot and dense, protons and neutrons are colliding and instantly being knocked apart in a rapid, frustrating dance. It's like trying to build a Lego castle on a trampoline during an earthquake. However, as the universe continues to expand and cool, a small window of opportunity opens up. Starting around the 3-minute mark, the temperature drops just low enough, but still billions of degrees, that the strong nuclear force can finally bind a proton and a neutron together before the next high-energy photon comes along to smash them apart. You are witnessing the formation of the first atomic nuclei. This is the solid historical fact of this section. About 75% of the resulting matter by mass is hydrogen nuclei, just a single proton, and about 25% is helium nuclei, 2 protons and 1 or 2 neutrons, with tiny trace amounts of lithium. Everything that happens for the next 13.8 billion years is built from these 3 lightweight elements, cooked up in the first 3 minutes. It's a very elegant, simple recipe. A curious detail here. While the universe is overwhelmingly made of hydrogen and helium, the theoretical conditions were right for a tiny, tiny fraction of heavier elements to form. But the time window was simply too short. The rapidly dropping temperature meant the cosmic cooking oven shut off before anything heavier than lithium could be successfully brewed. It's the universe saying, "Sorry, folks, closing time." This early nucleosynthesis wasn't capable of making carbon, oxygen, or anything that makes you possible. That job is reserved for the spectacular explosions of the first stars, which we'll get to soon. Historians still debate whether a hypothetical dark radiation component might have influenced the rate of expansion during this nucleosynthesis period, which could subtly change the final ratio of hydrogen to helium. You are watching a truly magnificent process where the initial conditions set the stage for all future chemistry. Imagine the frantic activity as trillions upon trillions of nuclei snap together, locking into place, the fundamental grammar of all matter being written in an energetic flash. Remember how dense and opaque the universe was in the first section. It's still dense, but it's slowly, inexorably, cooling. The protons and electrons are still too energetic to settle down and form neutral atoms. They're zipping around as a free-floating plasma, and this state prevents light from traveling freely, keeping the universe locked in darkness. You're still trapped in a bright, swirling fog that goes on forever, in every direction. The true dark ages are coming next. The universe is aging, though not by much. We've jumped forward considerably in time from those frantic first few minutes. Now, you find yourself floating in the cosmos about 380,000 years after the Big Bang. This is the moment everything changes. The transition from the glowing, opaque plasma you remember to the dark, transparent cosmos. Recall that dense, swirling fog in the last section. It was essentially a prison for photons, light particles, which were constantly scattering off free electrons and protons. It was bright, yes, but it was uniformly bright, like being stuck inside the core of a star. And there were no shadows, no direction, no stars to see. You're watching the temperature drop steadily due to expansion, and this is the crucial factor. The universe has finally cooled to around 3000 Kelvin, about 2700 degrees Celsius. That's still incredibly hot, far hotter than anything on Earth, but it's the magic number for the universe. The temperature hits this critical threshold. The positively charged protons, hydrogen nuclei, and the negatively charged electrons finally slow down enough for their electrical attraction to overcome their kinetic energy. They grab onto each other. You are witnessing the formation of the first stable, electrically neutral atoms, primarily hydrogen and helium. This process is known as recombination, which is actually a slight misnomer because the particles were never combined before, but the name stuck. This is the solid historical fact of the section. When the electrons drop into orbit around the nuclei, the universe fundamentally changes state. All those free electrons that had been scattering the photons are now locked up, suddenly making the universe transparent. The photons, previously trapped, are now free to travel in straight lines across the cosmos for the first time. They flood out in every direction, carrying the light of that last bright moment. You are watching the first light shine. A moment of profound liberation. This released light, stretched and redshifted by the subsequent 13.8 billion years of cosmic expansion, is what we detect today as the cosmic microwave background, CMB. It is literally the echo of the Big Bang, the most ancient light in the universe, filling all of space and still hitting your skin right now. It is incredibly uniform, yet a curious detail is that the CMB is not perfectly smooth. Tiny, fractional temperature fluctuations exist only about 1 part in 100,000. These are the density ripples, the subtle gravitational lumps that will eventually grow into all the stars and galaxies you see today. If the universe had been perfectly smooth, we wouldn't be here. Everything would have just diffused away. Thank goodness for those little density imperfections, or we wouldn't have any cosmic structure. As this last flash of light passes you by, the universe becomes truly, profoundly dark. This new phase is appropriately named the Cosmic Dark Ages. Neutral gas atoms fill the space, but there are no stars, no galaxies, and no sources of light, except for those now incredibly distant and fading CMB photons. You are floating in a void of cold, dark hydrogen and helium gas. It's a vast, silent, empty, and extremely dark canvas. Historians still debate whether this era was truly dark, or if hypothetical, exotic physics like the decay of dark matter created a faint, non-stellar background glow. Regardless, you are moving through a period where the seeds of the future, those tiny density ripples, are slowly, patiently waiting for gravity to do its slow, cumulative work. The stage is set for the birth of the cosmic structures we know and love. You are still drifting through the vast, cold emptiness of the cosmic dark ages. A billion years or so after the last section. Remember that faint starlight at the beginning? The CMB. That light is now incredibly redshifted and almost undetectable. The cosmos is filled with those neutral hydrogen and helium gas clouds, silent and still. This is the ultimate quiet before the storm. But beneath the surface, Gravity is relentlessly working its magic, patient and cumulative. Look closely into the darkest regions of space. The areas corresponding to those tiny density fluctuations you saw in the cosmic microwave background. The slightly denser pockets of gas, those fractional lumps, are acting like gravitational sponges. They are attracting more and more of the surrounding gas, slowly collapsing under their own weight. This process takes hundreds of millions of years, an eternity to us, but a mere blink on the cosmic scale. As the clouds collapse, they spin faster, and the central pressure and temperature skyrocket. You are witnessing the birth of the first true structures in the universe. These collapsing clouds are the stellar nurseries, and they are giving rise to a generation of stars, utterly unlike our Sunday. These are the legendary population 3 stars, the cosmic pioneers. The solid historical fact here is that these first stars were monumentally massive, perhaps 100 to 1,000 times the mass of our Sun, and they were made exclusively of the basic elements cooked up in the Big Bang: hydrogen and helium. Why? Because no heavier elements, no carbon, oxygen, or iron, existed yet to help cool the gas cloud, preventing it from fragmenting into smaller stars. It's like trying to build a complicated engine with only 2 kinds of screws. The gas cloud couldn't cool enough to make small stars, so it had to make gigantic ones. Finally, the core of one of these gigantic gas balls reaches the critical temperature, around 15 million Kelvin, and the immense pressure overcomes the electromagnetic repulsion between hydrogen nuclei. Nuclear fusion ignites. You see the universe's first true light source, a brilliant beacon bursting forth from the darkness. It's a moment of profound cosmic triumph. These stars burn with a furious, blue-white intensity, hundreds of thousands of times brighter than our Sunday. A curious detail about these population 3 stars is their ridiculously short lifespans. Our Sun will live for about 10 billion years. These cosmic giants, due to their incredible mass and fuel consumption, burn through their entire hydrogen supply in only a few million years. It's a spectacular, short-lived blaze of glory. Imagine buying a gigantic sports car that runs out of gas after just a few fast laps. It's impressive, but fleeting. You watch as these first stars, having synthesized elements like carbon, oxygen, and iron in their cores, finally meet their violent end. They detonate as magnificent supernovae. Some so powerful, they're called pair instability supernovae. The force of these explosions is staggering, spraying the newly forged, heavier elements, the metals of astrophysics, back into the surrounding space. This cosmic shrapnel, rich in the building blocks of planets and life, pollutes the pristine hydrogen and helium gas. Historians still debate whether all population 3 stars exploded as supernovae, or if some were so large they collapsed directly into massive black holes, seeding the centers of future galaxies. Either way, this recycling process is crucial. The universe is finally learning how to make complicated stuff. This enriching of the cosmic medium paves the way for the next generation of smaller, longer-lived, and more familiar stars to form. The Dark Ages are officially ending, replaced by the brilliant dawn of the first galaxies. The spectacular explosions of the population 3 stars have ripped holes in the surrounding neutral hydrogen gas, heating and ionizing it. You are now witnessing the process known as reionization, about 500 million to a billion years after the Big Bang. The dark neutral cosmos you remember from the Dark Ages is gradually being illuminated and transformed by the UV radiation from these new, powerful light sources. It's like turning on the first scattered street lamps in a previously unlit, endless city. But the light is just a symptom of the real action. Gravity is still pulling those enriched gas clouds and newly formed star clusters together. You are moving through a colossal, interconnected web of dark matter, the invisible scaffolding of the universe. This is the curious detail of this era. The visible matter stars, gas, makes up less than 5% of the total mass energy. Yet it's the invisible dark matter that dictates the grand architecture. These dark matter halos, vast spherical clouds of unknown particles, act like gravitational fishing nets, catching the newly synthesized metals and gases. As matter piles up within these halos, the star clusters merge, gas clouds collide, and the first coherent, large-scale structures are formed, the proto-galaxies. You are watching the ultimate cosmic construction project. These early galaxies are irregular, messy, and extremely active. They are often smaller than our present-day Milky Way, but they are absolutely blazing with star formation, churned by frequent, violent collisions. The solid historical fact of this era is that these early proto-galaxies frequently merge in a process known as hierarchical merging. Small clumps come together to form medium clumps, which then combine into the massive, spiral and elliptical galaxies we see today. You are watching a continuous, chaotic dance of growth. Imagine two great cosmic clouds rushing toward each other, their gas streams colliding, igniting bursts of brilliant star formation, and their central star clusters sinking towards a common core. It's like watching two giant, fiery whirlpools combine into one even bigger, more energetic vortex. Sometimes, the smaller galaxy is simply swallowed, a process called galactic cannibalism. These early galaxies are also starting to feed the most powerful engines in the universe, quasars. Deep in the heart of the largest proto-galaxies, the supermassive black holes formed either directly from collapsing population 3 stars or through rapid accumulation are now gorging on the surrounding gas and stars. As this matter spirals into the black hole, it heats up to incredible temperatures, emitting blinding jets of radiation that can outshine all the stars in the host galaxy combined. If the universe had a headlight switch, this is when it really got turned on, announcing the presence of mature galactic structures. Historians still debate whether these supermassive black holes formed before the galaxies around them or at the same time as their host structures. It's the classic chicken or the cosmic egg problem. But as you continue to drift through this swirling, merging, and radiating cosmos, you realize that the foundation for our own cosmic home is being laid. All this frantic activity is leading to the quiet, majestic spiral that will eventually house you. The universe is settling into its mature, galaxy-dominated phase. You have traveled billions of years, witnessing the universe evolve from a hot plasma to a cosmic web dotted with proto-galaxies. Now, we zoom in on a specific densely populated region of that web. The year is approximately 10 billion years ago, and you are floating within a particularly large, swirling cloud of gas, dust, and dark matter that is collapsing in on itself. This is the birthplace of our cosmic home. The gas and stars are not just collapsing randomly, they are spinning. As the material falls toward the center, the conservation of angular momentum causes the cloud to flatten into a majestic, rotating disk. Imagine a giant, slow-motion figure skater pulling in her arms. The result is a beautiful, flat spiral shape. You are watching the formation of the Milky Way galaxy. The solid historical fact here is that the Milky Way is not a single entity that formed all at once. It grew through accretion and minor mergers. You are seeing streams of smaller, satellite galaxies being ripped apart by the Milky Way's stronger gravitational pull. Their stars and globular clusters being absorbed into the growing disk and halo. It's like watching a cosmic snowball roll downhill, picking up fresh snow as it goes. A curious detail is that some of the oldest stars in our galaxy, found in the halo and globular clusters, are nearly as old as the universe itself, indicating they were formed in those early, smaller proto-galaxies, and were later absorbed. Our Milky Way is essentially a massive compilation of previous galactic histories. As the bulk of the gas settles into the disk, two main features emerge. the relatively flat, younger, and blue spiral arms, where new stars are still actively forming, and the older, yellowish, and dense central bulge. Deep in that center, matter has accumulated to such an extreme density that it forms the supermassive black hole known as Sagittarius A, which weighs about 4 million times the mass of our Sunday. While it's currently quiet, during this earlier, more active phase of galactic formation, it would have periodically flared as it consumed vast amounts of gas and dust. You find yourself in the mid to outer region of this young, vibrant spiral arm. The environment is still rich in gas, and the heavy elements, the metals that were forged in the supernovae of those long-dead population 3 stars. You remember, the constant gravitational churning within the disk, caused by density waves moving through the spiral arms, creates conditions perfect for the next stage. Historians still debate whether the Milky Way's spiral arms are semi-permanent physical structures, or if they are transient density waves, much like a traffic jam that moves even though the individual cars are different. This particular region, which will eventually become the Orion Arm, is still a dense cloud of molecular gas. This cloud, having been enriched with all the carbon, oxygen, nitrogen, and silicon from previous stellar deaths, is ready to give birth to a third generation of stars, including one very special, average star and its surrounding planetary system. You've positioned yourself perfectly to watch the ignition of our star. You are now in the midst of a spectacular galactic nursery, inside a dense molecular cloud, within one of the Milky Way's spiral arms, about 4.6 billion years ago. This cloud, having been enriched with the heavier elements from previous generations of stars, is gravitationally unstable. The constant churning of the galaxy, and perhaps a nearby supernova shockwave, a solid historical fact for our solar system's birth, finally triggers a rapid, localized collapse. As a particularly dense clump of gas and dust spirals inward, it begins to spin faster and faster, flattening into a great cosmic pinwheel called the protoplanetary disk. In the very center of this disk, where most of the mass is collected, the pressure and temperature reach a critical point. The core ignites with a flash of light. You are watching our sun come to life. A magnificent, slow-burning star, so different from those furious, short-lived population 3 pioneers. The young sun begins to shine, but it's still shrouded in a dusty gaseous veil. The heat from the core creates a temperature gradient across the disk. Closer to the sun, the heat is so intense that only materials with high melting points, like metals and silicate rock, can condense and form solid grains. This explains a curious detail about our solar system's architecture. The inner planets Mercury, Venus, Earth, and Mars are small and rocky, while the outer planets are gaseous giants. It's like a cosmic zoning law. No ice allowed in the hot inner neighborhood. You are watching the birth of the planets in a process known as accretion. Tiny dust grains collide and stick together, forming larger pebbles. These pebbles grow into kilometer-sized planetesimals, which then, like gravitational snowballs, sweep up more and more material. In the inner solar system, you see these rocky bodies collide, sometimes violently, sometimes gently, as they build up the cores of the terrestrial planets. In the outer, colder regions of the disk, beyond the frost line, water, methane, and ammonia ice can exist, providing much more material for the outer planets to accrete. This abundance of icy material allows Jupiter, Saturn, Uranus, and Neptune to grow into gas giants, their massive gravity sucking in huge envelopes of hydrogen and helium gas. The early solar system is a chaotic and violent place. You see planets forming, but you also see a constant barrage of collisions. A particularly famous one, the giant impact hypothesis, is what we believe formed our moon. A Mars-sized body, named Theia, slams into a young molten Earth. The impact is catastrophic, spewing a tremendous amount of molten rock into orbit, which eventually coalesces into our moon. It's a messy, violent process, but it is necessary for the final, structured state of our planetary system. Historians still debate whether a fifth gas giant might have once existed in our outer solar system before being ejected by a gravitational interaction with Jupiter. But you are seeing the final shape of our solar system solidify. The violent collisions lessen. The remaining debris is either absorbed by the planets or flung out into the far reaches of the solar system, forming the Oort cloud. The sun shines steadily. The planets are in their orbits, and on one particular third rock from the star, the stage is set for a truly unique and improbable event. The violent, formative years of the solar system are over. You are now orbiting a young molten Earth, roughly 4.4 billion years ago. The constant barrage of planetesimals has subsided, and the surface is cooling, forming a thin, rocky crust. However, the internal heat remains immense, driving intense volcanism that belches forth gases, water vapor, carbon dioxide, nitrogen forming the planet's second atmosphere. The first, lighter atmosphere was blown away by the young sun's intense solar wind. This is the epoch where the ingredients for life are finally brought together. You see, the oceans form as the Earth cools below the boiling point of water. The vast water vapor, released by volcanoes and delivered by icy comets from the outer solar system, condenses, falling as rain for millions of years. This deluge fills the basins and creates the primordial soup. This is a solid historical fact. The presence of liquid water for billions of years is the most crucial prerequisite for Earth's life. You observe the young Earth, still spinning incredibly fast, resulting in days that were only a few hours long. The tides, driven by the massive, nearby moon, are far more extreme than today, dramatically mixing the chemicals in the shallow seas and tidal pools. These intense, cyclical changes, wetting and drying, heating and cooling, provide the energy and concentration needed to drive complex chemical reactions. A curious detail of this era is the sheer energy driving the chemical synthesis. There's no protective ozone layer yet, so the sun's powerful UV radiation bombards the surface. Coupled with geothermal heat from undersea vents and lightning from massive storms, this energy is cooking the primordial molecules. Simple inorganic molecules are spontaneously reacting to form complex organic building blocks: amino acids, fatty acids, and nucleotide bases. You watch as these organic molecules, floating in the warm, mineral-rich water, begin to self-organize. Imagine tiny, floating oil droplets, lipids, spontaneously forming membranes, creating the first simple, enclosed compartments. These membranes are crude, leaky, but they provide a protected internal environment. Inside these early protocells, the magic happens. The complex molecules, particularly RNA, ribonucleic acid, which can both store genetic information and catalyze chemical reactions, begin to self-replicate. This is the origin of life, the ability for a system to reproduce itself imperfectly, allowing for evolution. You are witnessing a biogenesis, the transition from non-life to life. It is not a sudden lightning bolt moment, but a long, slow chemical journey. Historians still debate whether life originated in warm, shallow ponds, deep-sea hydrothermal vents, or even within mineral pores in the deep crust. Regardless of the exact location, the end result is the same. The first single-celled, self-replicating organisms arise. They are simple, prokaryotic cells, lacking a nucleus, but they are alive. The universe, which started as quarks and leptons, has now figured out how to write its own story in the language of DNA, or its early precursor, RNA. You are now fast-forwarding through a vast expanse of time, nearly 4 billion years of Earth's biological history. The simple, self-replicating molecules you saw emerge in the last section have evolved into the last universal common ancestor. and then diversified into an array of simple, single-celled life. This early life, thriving in the oceans, starts to fundamentally alter the planet's chemistry. The solid historical fact that dominates this billion-year stretch is the rise of photosynthesis. About 2.4 billion years ago, organisms like cyanobacteria developed the ability to use sunlight to convert carbon dioxide and water into energy, releasing oxygen as a waste product. This was the original environmental catastrophe, ironically dubbed the Great Oxygenation Event. You watch as the newly created oxygen, a poisonous gas to the existing anaerobic life, bubbles up out of the oceans, first saturating the minerals, creating vast iron oxide deposits, and then flooding the atmosphere. This radically changed the planet, leading to the extinction of much of the early life and paving the way for aerobic organisms that could harness oxygen's potent energy. The timeline accelerates. Life spends its first 3 billion years as mostly single cells. But around 1 billion years ago, a curious detail emerges. Simple cells start cooperating, combining to form eukaryotic cells, cells with a nucleus, and organelles, and eventually, the first multicellular organisms. It's like the universe has finally figured out that complexity is easier with teamwork. You witness the Cambrian explosion, a relatively short period about 540 million years ago, where almost all major animal phyla suddenly appear in the fossil record. Life explodes into diverse forms in the oceans, evolving shells, claws, and eyes in an evolutionary arms race. As you zoom closer, you see life conquering the land. Plants develop the ability to stand upright and retain water, followed by insects and eventually vertebrates. You watch the rise and fall of dominant species, punctuated by mass extinction events, cosmic impacts, massive volcanism, and rapid climate change. You see the dinosaurs rule for 180 million years before a rogue asteroid impact triggers their sudden demise, except for the lineage that became birds. Then comes the rise of the mammals and the primates. You speed through the last few million years, watching hominids emerge from the African savanna, developing larger brains, using tools, and finally, mastering fire. You see the emergence of Homo sapiens, our species, spreading across the globe, developing language, agriculture, and civilization in a mere geological blink. Historians still debate whether human-level intelligence was an inevitable outcome of biological evolution on a stable planet or a highly improbable, rare accident influenced by numerous environmental factors and contingency. As you settle into the present day, you see human civilization flourishing, a direct product of the quarks, gravity, and starlight you witnessed billions of years ago. We are literally dust from exploded stars, arranged by chance and time to observe the very process that created us. Now, the biological journey ends, and the final, vast cosmic chapter begins. You have reached the present day, a beautiful, fleeting moment in the universe's 13.8 billion year history. You see our sun, about halfway through its stable life, shining warmly, and the earth teeming with life. But your journey must continue into the incomprehensibly deep future, the ultimate cosmic endings. Remember those giant, short-lived stars from the early universe. Our sun, being a modest star, will take far longer to meet its fate. About 5 billion years from now, the solid historical fact is that the sun will exhaust the hydrogen fuel in its core. Without the outward pressure of fusion, gravity will begin to win, causing the core to shrink and heat up dramatically. This increased heat will ignite a shell of hydrogen outside the core, causing the sun's outer layers to puff out and cool, transforming it into a red giant. You watch as the sun swells to an enormous size, swallowing Mercury, Venus, and possibly even engulfing Earth in a fiery demise. It's a sad, inevitable ending for our solar system, After a relatively brief period as a red giant, the Sun will shed its outer layers, forming a beautiful, expanding shell of gas called a planetary nebula. The remaining core will shrink into a dense, hot cinder called a white dwarf, slowly cooling and fading over trillions of years. But the universe itself continues. A curious detail is that, as the universe relentlessly expands, galaxies are increasingly driven apart, because the expansion of space, driven by dark energy, only affects objects not bound by gravity. Our local group of galaxies will remain, but all other galaxies will eventually recede faster than light, becoming unreachable and invisible. Hundreds of billions of years from now, future astronomers on a lone galaxy will look out and see nothing but an empty void. Unaware of the vast cosmos that once existed, the universe enters the stelliferous era's twilight. Over the next 100 trillion years, all existing gas clouds will be consumed by star formation, and new star births will cease entirely. The current generation of low-mass stars, like red dwarfs, which have lifespans of up to 10 trillion years, will be the last beacons of light. Once they fade, the universe plunges into true darkness, the degenerate era. In this new, cold epoch, only stellar remnants remain: white dwarfs, neutron stars, and black holes. Even the protons that make up atoms, the same protons you saw form in the first 3 minutes, are not eternal. Historians still debate whether protons are completely stable or if they decay with an incredibly long half-life, perhaps on to the power of 34 years. If they do decay, the last structure of matter will vanish, leaving only an ultra-dilute sea of electrons and positrons. Finally, we reach the far, far end, the black hole era and the ultimate dark era. Black holes, the devourers of stars, are also mortal. They slowly evaporate via a quantum mechanical process called Hawking radiation. You watch the largest supermassive black holes, weighing billions of solar masses, take an astonishing on to the power of 100 years to finally dissolve into a final, weak flash of photons and elementary particles. The final state of the universe, whether it's a heat death cold, uniform expansion to absolute zero, a big rip expansion tears apart even atoms, or a big crunch recollapse, remains the subject of intense research. But in the most likely scenario, you are left in an unimaginably vast, cold, empty void, where the distance between the last remaining particles is measured in light years, and the temperature is a fraction above absolute zero. The energy of the Big Bang, which started this magnificent story, is finally spread so thin that no change, no work, and no life is possible. It's the final, silent whisper of time. Now, let the immense scale of that final journey gently recede from your mind. That ultimate, cold silence is trillions upon trillions of years away, a time so far removed from your own immediate reality that it can feel like a dream, a distant, quiet echo. You can allow the images of the exploding stars, the merging galaxies, and the incredible dance of atoms to slowly dissolve into the peaceful darkness behind your eyelids. You are here, now, warm and secure, a precious arrangement of matter forged in those ancient, fiery stellar furnaces. The story of the universe is a cycle of birth, destruction, and rebirth. But you are resting in its glorious middle chapter. Feel the weight of the blanket, the soft rhythm of your own breath, and let your body sink deeper into relaxation. The forces of the cosmos that created the stars and the oceans are now simply working to ensure your peace. There is no urgency in the vastness of time, and there is certainly no need for you to hold on to these thoughts. Just float freely, knowing that for tonight the journey is over. The universe is waiting for you, but it can wait until morning. Sleep well, friend.